Welcome to the Center for Meteorite Studies at Arizona State University. My name is Dr. Devin Schrader. I'm the interim director of the Center for Meteorite Studies, and today I'm going to take you on a tour of the meteorite vault and through 4.5 billion years of solar system history.
So welcome to the Meteorite Vault of the Center for Meteorite Studies at Arizona State University. We have one of the world's largest meteorite collections that's based at a university in the world. We have specimens of over 2,000 distinct meteorites, and that's 2,000 distinct objects that were seen to either fall or were later found. And so falls are objects, meteorites that are seen to fall, observed by someone, and then later picked up. Finds are meteorites that could have been on Earth for a day but was not seen to fall, or meteorites that have been on the Earth for millions of years and were later collected. Of those 2,000 distinct meteorites, we have over 40,000 individual pieces. So from some meteorites, we have hundreds of pieces from that fall or find. Other meteorites, we only have one piece. So meteorites can be categorized into three major types: stony meteorites, stony iron meteorites, and iron meteorites. So probably the most famous stony meteorite is the Allende meteorite, which fell in Mexico in 1969. Over 2 metric tons of material fell, so that gives scientists a lot of material to work with. This meteorite has been heavily studied and researched at ASU and around the world, and I myself have also studied this meteorite. These are some large specimens that we have not cut and probably never will because they're just beautiful and important historically. The one on the top shelf that you can see right now is still covered in mud and grass from when it first impacted the ground. So that's a pretty spectacular specimen. But to learn about the meteorite, we have to cut, polish, and look at the inside and analyze the individual components of the Allende meteorite. So now, I'll take you over to a slice of the Allende meteorite to get to see what's on the inside. So this is what the Allende meteorite looks on the inside. So we cut and polish it with a diamond encrusted saw and then polish it down to a nice mirror polish. And so you can see there's a lot of different objects in this slice. There's these large white inclusions. Some of them look kind of funny like amoeboid, and then there's a lot of kind of bluish gray material. First, I'll talk about the large white inclusions. Those are called calcium aluminum rich inclusions, and those are actually the first material to condense into a solid at the beginning of the solar system. So when the solar system was just hot gas and dust, these were the first solids that condensed out, just kind of like rain droplets condense out of a rain cloud. And so by dating these, we actually know how old the beginning of the solar system was. And work done here at Arizona State University concluded that these objects are 4.567 billion years old. So when you hear about how old the solar system is, studying these objects is how we know that number. The material in between the CAIs is a collection of chondrules. Chondrules are roughly spherical objects, but in a slice they look like circles. And these are objects that formed from kind of little dust balls that were freely floating in the early solar system that were melted to high temperatures to where they almost completely liquefied. And those formed mostly after calcium aluminum rich inclusions until about 4.5 million years after CAIs formed. And so we can study them to learn about the time after calcium aluminum rich inclusions formed. And then material in between the chondrules and the calcium aluminum rich inclusions, it's a bit hard to see, but everything that isn't a round little circle we call matrix. And that's fine-grained material, and that's really fascinating to study. That was material that did not get up to those high temperatures that formed calcium aluminum rich inclusions or chondrules. And so in the matrix are preserved in some carbonaceous chondrites, which Allende is a carbonaceous chondrite. Sometimes there's organic material preserved, so not life, but organic molecules. And there's also objects called pre-solar grains, which are little dust grains that formed around other stars before our solar system existed. Yep. So next we have stony iron meteorites. And these are meteorites that come from asteroids that got up to high temperature and melted throughout the asteroid. And so heavy elements such as iron sank to the center of the asteroid, whereas lighter things like rocky material floated to the surface. And so stony iron meteorites, particularly this one, a palisite, we think represents the core mantle boundary in these melted meteorites, or these melted asteroids. And so here we have a nice mixture of stony and iron material. So this is the stony material. This is an iron magnesium silicate called olivine. And on Earth, we have olivine, and it's a deep mantle mineral. So by studying meteorites, we can actually help learn about our own planet, about how our own planet may have formed. And then this shiny material is actually iron nickel metal. And so the core of an asteroid we think is going to be mostly iron nickel metal, but these pallasites are a mixture of iron nickel metal and this deep mantle mineral olivine. So we think this represents the core mantle boundary of an early formed asteroid. So the last major type of meteorite we have are iron meteorites. And these are meteorites that also came from melted asteroids, asteroids that formed at the very beginning of the solar system with enough heat through radioactive decay to melt. So the heavy elements like iron and nickel sink to the core of the asteroid, and this meteorite we think does represent the remnant of an ancient asteroidal core. So the pattern you're seeing there, the crisscross patterns, is called the Widmanstätten pattern. It's actually the crystal structure of iron nickel metal. By studying it, we can learn about how slow this asteroidal core cooled. This one in particular we think cooled between around 10 degrees Celsius per 1 million years. It took a long time to cool down from high temperature, about 1,000 degrees Celsius or more that it got up to. And so by studying these iron meteorites, studying these ancient asteroidal cores, we can actually learn about early planetary differentiation and what our own planet may have gone through during the first stages of melting. And since we cannot get to our own core on Earth, by studying iron meteorites, we can also learn about the core of our own planet.
I'm Dr. Gemma Davidson. I'm a research scientist here in the Centre for Meteorite Studies at Arizona State University. And in addition to meteorites from asteroids, we also have a large collection of samples from the moon, such as this lunar meteorite here. This is Northwest Africa 5000. And we also have pieces of Mars. So this is a famous Martian meteorite called Los Angeles. And then here in my hand, I have a Martian meteorite. This is Northwest Africa 7034. This is also known as Black Beauty. You see it's a very, very dark meteorite. It's also quite beautiful. And this is the only meteorite that we know of that is most representative of the Martian crust. So here what I'm holding in my hand is a piece of Mars's crust. And we've been doing a lot of research on this here at ASU in collaboration with Professor Meenakshi Wadhwa, the director of the School of Earth and Space Exploration. We've been working on this sample to investigate water on Mars. So you may have heard that, these different robotic space missions have found traces of water on Mars. Well, this sample gives us a chance to analyze that water in the lab. So in these different components of this meteorite, there's trapped very, very tiny amounts of water on the parts per million level. So it's a very dry rock, but there is water trapped in the minerals there, and we've been able to analyze that water to determine what the water composition of Mars's crust is, and that can tell us about where Mars got its water. Thank you for joining us today for the tour of the Meteorite Vault at Arizona State University's Center for Meteorite Studies. We hope you enjoyed it and that you'll come visit us sometime in the future.